So this session is kind of the first sort of deviation. This one can probably be taught really almost in any scientific context and has nothing to do with biochemistry. So we will deviate a little bit from our biochemical theme of this morning. The reason we wanted to have this session is because it's often important to understand where some of the software is coming from. And in a scientific context, many of the programs that we use are not implemented for whatever reason on Mac or PC. And so how many people have had a chance to sort of run into one of those software programs where, you know, there wasn't a version that easily ran on Mac, there wasn't a version on PC? Anybody have a software like that? Okay. Yeah, go. What was the software? Yeah. So particularly if you're programming, lots of tools exist to develop software on Windows and Mac operating systems. However, many of those programs cost money, and if you're making, you know, Microsoft and Apple both want to profit on the fact that you're selling software for their system. And so, you know, if I were to purchase a copy of Visual Studio, at least if I were to purchase it back when I was around, or when I was in high school when Visual Studio was still a thing, you know, you could spend hundreds of dollars for that piece of software. And so because of this, lots of software in the scientific community, you know, if the federal government gives you money to study molecules, you don't want to spend all that money, you know, developing software and paying it to Apple or Microsoft. So lots of scientific software is developed kind of on a sort of shoestring budget, and they're using sort of free software that they can implement programs in, and that's where Linux comes in. So many of the programs that you might use, particularly if you're going to do any kind of advanced work, might be written in the Linux operating system, and there might just not be a good alternative for Windows. That's gotten better probably in the last 10 years or so. More and more software is appearing on Windows and Linux or Windows and Mac, and conversely, Windows and Mac have both tried to make strides in making their software more accessible to scientific users, because this has been a problem for many, many decades. But I think it's still very good and handy to know a little bit of Linux operating system and what it is, so that you're not terrified if you encounter it. There's a lot of great things about Windows and Mac, you know, software, but you know, chances are you're going to come across something where you're going to be using some Linux or a Linux operating system. In my lab, it's all the NMR processing, right? And so you know, the main guy who writes the NMR processing software, he's just kind of he's very stubborn, and he refuses to do something that would work on Windows. And so he has a Linux version, he has a Mac version, but if you're trying to run NMR pipe, at least up until recently, on Windows, you know, you were kind of out of luck. And some people have sort of recognized this, and they've actually packaged all this stuff together so that you could go online and download a virtual Linux system with a lot of the software already installed, that you don't have to worry about software maintenance and whatnot. This is not quite so extreme, so we're going to sort of set up an environment today that allows you to run Linux programs on your Windows or on your Macintosh PC. But you can go the whole hog and say, okay, I'm going to wipe my operating system and install Linux on my Apple or on my you know, IBM compatible computer and do it that way too. I wouldn't recommend that. Even my lab, we still use a lot of Windows because, frankly, we haven't really found a better alternative to Office or Adobe Illustrator or Adobe Photoshop, and those don't run so easily on Windows or on Linux. Okay, so you know, when we think about operating systems, an operating system is the base level of hardware that makes your computer work. And so oftentimes when you guys think about operating systems, you're thinking about the graphical interface. And that's an important part of any operating system. I mean, that's the part that you know, interface with, for lack of a better word. But the reality is that this is actually mostly fluff, right? So this is just some some tools that allow you to control files and open programs and move things around and potentially communicate with other computers on the network. But really the bare level of the operating systems, and when computer scientists speak about operating systems, they're talking about the software that basically runs at the lowest level of the computer and allows a program to say, hey, I want to open a file. And the operating system has to say, okay, I know how files are stored. I know where files are stored. So if you, the software package, want to open this file, which I know exists somewhere on my storage system, I can tell you how to get to that file, and I can tell you this is how you have to talk through me to interface with that file. And so the operating system is really the gatekeeper between all of the software that runs on your computer and all of the hardware that software needs to interact with. And so, yes, modern operating systems have evolved this very handy interface so that you can sort of see pictures and have nice graphical presentations. But 20, 25 years ago, this is what we were dealing with, because really the main goal of an operating system is just to manage software and allow that software to run efficiently. And so because of that, there's multiple different solutions to this. Windows and Macintosh OS X are two big ones. They're the ones that are most commercially popular. Some of you might have heard of some alternatives that have existed in the past. So OS 360 was one that was IBM had for servers. OS 2 was one that was popular back when I was in high school that was an alternative to Windows. BOS was one. But we're going to sort of focus today on Unix and or Linux, right? And so when I use Unix, I kind of mean them in the same way. Technically speaking, and those of you who might have lots of experience with this will recognize that Unix refers to a commercial operating system that was developed. It was closed source, and it was sold just like Mac or Windows was. Linux is basically, I wouldn't say it's a clone. It looks very similar to Unix, but it was developed as an open source project, and it doesn't really have any of the commercial restrictions that Windows and Macintosh would. And so, we talked briefly at the introduction why we would do this. Why scientific software would be implemented in a Unix or a Linux-like environment. Again, less true today, but certainly even when I started as a faculty member, before Windows, honestly, Windows XP was kind of the first real operating system that I was able to take Windows seriously, just because before that it would just crash. And I still have a Windows 98 machine. I still have a Windows 3.1 machine. Not with me, but at my in-laws, that I still start up every once in a while. And it's incredible. You open up the browser on Windows 3.1 and you might get 5 minutes before it crashes, right? And so computers back in the mid-90s, no matter what people might tell you, kind of sucked. And Windows has come a long way and is very much more stable than it used to be. But even so, my lab server can be up for months at a time without restarting. That's something that's rarely true of my laptop, even though my laptop is a great system. I love it. So Linux, and when you're thinking about scientific software that needs to do calculations that might take a week or 2 weeks, you don't want to lose a week's worth of calculations because some program decided to update the software and crash the entire computer. Right? So the stability of Unix and Linux operating systems is actually one of the main reasons that people use this. And even today, most sort of server environments are still running Linux and Unix because, again, you don't want to run the risk that something is going to happen and the machine dies. Right? Linux and Unix operating systems were also the first operating system to do multitasking. They were also the best for many years. I mean, so both Windows and Mac operating systems did what was called cooperative multitasking, where one program would have to relinquish control of the computer for another program to start running. Whereas Linux and most Unix operating systems, I want to say from the very start, but don't quote me on that, have used something called preemptive multitasking, where the operating system can basically just say, look, you're done running, I'm going to let something else run. And if you think about programs that might run away and start taking over your computer and not let you use things, it's really nice to be able to have the operating system say, hey, look, you're done, and be able to stop it in a graceful manner. And so Linux has always done multitasking at least as good, if not better, than Windows and Mac. The flexibility offered by Linux is another big reason. So again, sometimes all that graphical cruft that you're seeing here is really helpful, but if you have a computer that's basically only ever going to be accessed over the internet and is only ever going to have to run calculations, you know, the more stuff you have running on your computer, holy Moses. I'm going to go ahead and assume everything is okay until something comes crashing through that wall. But whoa, we get some construction in chemistry, but we've never heard anything like that. So the more stuff that you have running on your computer, the more likelihood something is going to crash and throw your computer into error state. So Linux gives you the flexibility to say, hey, I don't want to run any of that graphical stuff. Just give me the core stuff that I need. And Windows and Mac have gotten there, I mean, over time. But still, I mean, the main way that you would install Windows or a Macintosh operating system would be with the graphical environment, and that would be the primary intended way for you to control all the settings, for example. Linux also has this unique tool where it has this scientific focus, in part because it's free and scientists are generally cheap. It's usually available, and so scientists are free to write software, and for many, many years, you know, lots of scientific programs were released on Linux exclusively. The barrier to creating a program in Linux is much, much lower than it is in Mac or Windows systems. And so that was demonstrated by the compiling C code. I can go on Linux and pretty much guarantee that any Linux system I log into is going to have a C compiler. It's probably going to have some ways to edit text files. And so in principle, I could start writing a C code or a program in C, you know, as soon as I log into that Linux system. The likelihood that I could do that on a Windows system is almost next to nothing. On a Mac, most Macs nowadays do have a C compiler installed, but it's a little bit harder to get to. And I bet those of you running the Mac, unless you've done it before, don't know how to do that. So the other thing is Linux and Unix generally handles lots of files well. And so in a scientific setting, I might have 1,000 data sets, right? And that's not hard, right? If I set a spectrometer or I set my little UV vis system to just collect a spectrum every second or every 10 seconds, it's very easy for me to generate, 1,000, a couple 100,000 traces of UV spectra. And if I have 1,000 files and I need to rename them, if you want to do that in Windows, you're basically sitting there clicking on it, typing the new name, clicking on. Imagine doing that for 10,000 files, right? Now again, there's ways that you can get around that for Windows, but that's kind of the default way to deal with things. In Linux, there's very powerful scripting tools that you can rename files in about 2-3 seconds. And then finally, just historical reasons. Scientists grew up around the Linux and the Unix community. Actually, before Linux, it was VAX or the VMS operating system. And so there's a lot of things that are out there that scientists have historically been very comfortable with Linux. And so more and more your generation and the future generations will probably be much more comfortable with Windows or Macintosh, but there's still a lot of vestigial stuff sitting out there that if you want access to, you're still going to have to learn a little bit about Linux. Okay, so where did it come from? Again, I've hinted at this fact that there was something called UNIX that had existed for probably 40, 50 years almost at this point. And back in the 90s, this gentleman named Linus Torvalds decided he wanted to be able to teach his students and things like that an operating system that would be like UNIX, but he wouldn't have to pay for, and he could show them what the source code looked like. And so he actually developed a program called Minix, or I guess somebody else had developed Minix, and Torvalds took Minix and developed it into Linux, which is sort of the starting point for what we have today. Now, today, Linux is it's developed by hundreds, probably even more, of software developers, and it's very much a team group project where lots of people are contributing at any given time. Back in the day, it was sort of his pet project, and Linus is still very influential in sort of directing the future. But the earliest version of Linux sort of came out to the world in 1994. I think I started using it probably around I think it was the 1.5 or 1.4 iteration. So I started using it in high school, which was many, many years ago, back in the 90s. And honestly, I had no idea what I was doing. Just a friend came over and installed it on my computer, and I said, oh, that's fun. And so it's been a long time for me. And that's one thing to note here, is that we can get you sort of proficient in Linux, but it's going to take a little while to get expert in it, and as with anything. Today it's used on lots of computers, particularly servers. Lots of the web is implemented on a Linux system, again, because of its stability. But there's many, many people working on sort of maintaining it, as well as the operating system and the other pieces of the operating system. And so when I talk about Linux, I'm really talking only about the kernel. And so remember, we talked about operating systems having these different parts. The kernel is the name of that executive piece of software that basically controls access to the hardware. And so Windows has a kernel, Macintosh OS X has a kernel, Linux has a kernel, and then all the stuff that you see, the graphical environment, the web browser, the command line interface, if you use one, the Word, well, that's not really, but all of the sort of extra interface that you work with is implemented on top of that kernel. And so just like with Windows, and there's like a command line or a graphical interface, there's the same thing in Linux, where when you install a Linux operating system, you're generally getting the same kernel, but any number of combinations of programs to run on top of that kernel. And so some of those will make, if you talk to the real Linux dorks out there, they'll show you these pictures of, ooh, look at my window. If I move it with the mouse, the window sort of trickles with like a waterfall, or they'll show you all these weird graphical effects. I'm like, great, I just want something that runs my programs. And so, but you can install different types of windowing environments. You can install different flavors of the command line interface, which we would call shells. And even simple utilities might be different that would be written on top of the Linux kernel. And so if I run Ubuntu, which is what my lab runs, the distribution that my lab runs, and I go down to the NMR facility and all the computers there run a distribution called CentOS, they're going to have different programs. One of them is going to have one default web browser. The other one might have another default web browser. But they all come with different sort of stuff. And because of that, you end up with these distributions where you have lots of people envisioning what an operating system should be, and they're all built on the same kernel, but they have different user experiences that come along for the ride. And so we're not going to go into all the distributions. This is basically a map of what you're dealing with. It's a ton, right? So this is almost like, oh, I want a new distribution. Well, go fork one. And because of that, things can get very confusing very quickly. We'll talk about the three main distributions that you're going to encounter, but the oldest one that is one that probably you won't encounter is called Slackware. This is the one that I used when I was in high school, and it's somewhat of a pain to manage, I got to be honest. But because of that, people saw, oh, I can improve it, and without fundamentally changing the operating system, they make some tweaks. and all of a sudden you have a new distribution that's based on an old distribution, and that's called, again, forking. So yeah, it's not like The Good Place. It's actual forking. So, and then at the same time, some distributions died out, right? So, you know, if 10 people in the world are using some weird distribution, there might not be a good reason to keep maintaining it, right? And so the history has sort of favored those distributions that were more user-friendly, that were more upgradable, and, you know, the distributions that were a real pain to manage, again, it's just not going to catch on. People have other things they want to do. They don't want to become operating system experts. And so these are the kind of 3 ones that you're probably going to come across with. CentOS, like I said, it's written to be very, very stable, but that stability comes at the expense of the fact that you might not have the latest version of the Firefox browser, for example. Right? It's designed to run for days, weeks, even months at a time without having to be restarted. Ubuntu is what I've chosen for my lab. I think that's what a lot of people use Linux for. It's a user-friendly, fairly easy to upgrade. It has a good mix of let's you know, have recent versions of software in them, but you know, we don't have to. But we want to still be fairly stable so that users can have a consistent experience. And then the final one that you might come across is Debian. And so this is you know, kind of the most cutting edge. As soon as a software developer releases a new version, they're encouraged to put it on the Debian stream, and that way it gets pushed out onto the computers. But if somebody, you know, accidentally includes a bug, well, then you might be running buggy software, and that might affect your experience. Now, again, we're not going to go over all this. This is here if you're interested. Here are some others that you might be interested in, but you can read this at your own sort of expense or in your leisure time. And so when we think about Linux versus Linux-like, you know, I've hinted at a couple of times that your Macs, if you're running a Mac operating system, you actually have a lot of the tools that would make your sort of experience, or could make your experience, look very much like a traditional Linux experience. Right? And so all of that sort of command line, or all of that graphical stuff that you're used to, is actually built on a command line interface that is, or at least can be made to look very much like a traditional Linux environment. And to me, that's probably the main advantage that Macintoshes have. I mean, I think that they're great, nice pieces of software. If I didn't know Linux as well as I did, I probably would have a Mac. Because to me, that would be much, much easier than trying to go and do what we're about to do with our Cygwin or install Linux as a virtual machine. And that's because, again, when we think about this executive sort of base level piece of software, they all have to do the same things. I mean, they all have to allow the computer to say, access the hard drive. They all have to allow the computer to say, hey, I need to send something out to the network. And so because of that, people have developed standards, and these are called the POSIX standards, that sort of implement how computers need to interface with the hard drive. And you know, dirty secret is that Mac, Windows, and Linux all implement this POSIX standard in some way. And so you can use a computer, and if you wipe away all of that sort of fluff or graphical stuff, and have the right software running on top of it, you can make them all look pretty much the same. It's just that that graphical stuff is really what lots of users are conditioned to expect and to appreciate in terms of ease of use. But Mac operating systems are built on this XNU kernel. So again, Linux has the Linux kernel, Mac has the XNU kernel, Windows has a Windows kernel, but and I don't know if those of you following the news, there have been some interesting developments. They're adding they have a Linux subsystem where they're actually trying to develop true software compatibility. So if I take a binary that was working on Linux, copy it over to my Windows system, and just run it, it should work. And that's what they're sort of working towards. And so when this actually goes live and hits prime time, and you can actually get it on your systems now, it doesn't support everything, and so there's some limitations, and so that's why I say it's not at prime time. But this might be a game changer, right? So if I can go to my lab and say, here, because most of my lab, I love them. You guys are awesome. But they don't know Linux any more than you guys do, right? So, they're all struggling with the same kinds of problems. Okay, my advisor gave me this computer that has this weird operating system on it that I've never seen before, and frankly hadn't even heard of until I got to graduate school. Is that right, Joanna? Yes. So, they're on the same boat. If we could get a system where, hey, everybody knows Windows, maybe not everybody likes Windows, but it can run all the software that we would need, well then, that might change things substantially, because now people can be comfortable doing the software that they need to run, but they could also be running other software in an environment that they're very familiar with. And so if you're interested in this is this recent article that talks about how Linux or Windows is adding this graphical subsystem. Until that happens, you're kind of stuck doing what we're going to be doing today. Mac, it's way easier. It's basically you install software. You guys could probably be doing this while I'm talking if you just go to XQuartz and install the program. But for Windows, we've got a little bit more to it. And so, okay, so this is great. I mean, this is kind of our history of where things were. Again, Unix came out. Linux was eventually kind of a derivative of that. But then this is kind of the context where you can see how, where Linux fits into Mac operating systems and then the Windows development. Again, I was using this, and I pretty much have used all of this. But, the original Macs, as much as people like to talk about the original Macs, they were not fun to use either. And they would crash almost as much as Windows did. And the big advantage was that you didn't have all the viruses and stuff written for them. So, but 2001 was a big year because that was also the year Mac OS X came out and Windows XP. And those were really, really good operating systems. I wouldn't use them today, but at the time they were great. Okay, so this is great. Lots of history about operating systems. Mostly you guys don't care. And that's fine, I get it. I feel like we have to give a little bit of context so that you can sort of appreciate what we're going to do. But the main goal of this session is to get you guys to a state where your computers are running a program called Cygwin, which is it's a Linux emulator to a certain extent, so you can have a command line interface that looks very much like Linux on your Windows computer. And then moreover, it allows you the remote graphical applications. And that's kind of the key thing that I think is the really unique thing that Linux has that Windows really doesn't have and Mac only has because it copied off of Linux. And so envision this. So my computer has this program called Kinomics, right? It's a metabolite analyzer for NMR spectra. And so you can load up your NMR spectra, and these can be very complicated NMR spectra, and it will go through and try to intelligently identify what compounds are in that NMR spectra and quantify how much of each compound there is. So if I give it a treated blood serum, there's literally going to be thousands of metabolites in there, and it can go in and approximate how much, for example, glucose or alanine or some of the other compounds that you would normally expect to find in blood. And it would tell me, oh, your glucose concentration is 5.8 millimolar, alanine is around 1.5 millimolar, something like that. That software is not cheap, right? And we can't afford to buy a copy for every student. So imagine this. My students can log in to a central server, and they can't all do it at once, but I can keep one copy of the software on that central server, and if they're at their desktop or back in their apartment, anywhere that has a reasonably fast internet connection, they can run the program on my server. The licensing people don't care because it looks like it's running on my server, but all the graphics are broadcast over the internet so that they pop up on my student's desktop. So they can be running the program, in my lab, which could be tens or even hundreds of miles away, and be able to see all the windows and the graphics of this genomics software, that now they can use that and they don't have to come into lab and use that system, or if one of them wants to sit at their desk while they're using it, they don't have to move across the room. Not that that's a huge burden. And so this is the advantage that Linux gives you, because you can broadcast that graphical interface through the network and run software on one computer and see it in the graphical state on another. And so that's going to be our goal today. If we can do that by the end of this session, I will have considered this success. Actually, if we can do it probably for 80% of you, because there's always going to be people that have problems with their computer, or their computer has a virus on it, or their computer is so slow that they just can't get it done by the time of this session is over. But we're going to do our best. Now, while we're doing that, I'm going to show this to you guys. So if you're running a Mac, this is what you should be doing. You can do this for 5 minutes and spend the rest of the 20 minutes that we're going to spend for the Windows users. You can be laughing at them. Go for it. You have my permission. Basically, what you want to do is you want to download this program called XQuartz, and it installs like a standard Mac program. It's a DMG. You double-click it. You double-click on the XQuartz software, and it should go and install. I don't have a Mac. I've tried this, I think, within the last 6 months on a Mac that was a friend's, and it should work. But I'm taking on faith that nothing has happened in the last 6 months. And then for your file software transfers, because again, just because you're looking at the graphics doesn't mean you have access to the file system. You're still going to need to transfer files back and forth between your computer and the lab server or wherever you're going. You want to download either Fugu or Cyberduck. Cyberduck is probably a little bit newer, but it's also a little bit slower. And so, your choice. For PC users, we're going to basically work through, or you guys will hopefully be able to do this while I walk around the room. We're going to work through that installing Cygwin software. And so this is where we're going to basically go through. I have it on here. And so this is, so this is where you would go to this worksheet, which again, you can get online. It should look something like this. It's a lot of reading, but you should be able to follow the step-by-step directions without reading the whole thing. I encourage you, if you're going to read it tonight, because it should be great. I think it's as helpful as I could possibly make it to be. And we're going to meet when the PC users and the Mac users are done. I'll be walking around helping you guys figure this out. And the end goal is to use that email that you should have received this morning if you don't already have an account on my lab system. And so if you don't have an account on my lab system, I've given you a temporary account just so that we could sort of play and experience what that's like. Obviously, if you're in my group or working in my lab, you already have this, so you didn't get an email. But we're going to try to meet and then hook up and try to see what we can all do on that system. Okay, so I think here's where we're going to break, and we'll come back and we'll do this. So start playing. I'm going to walk around and help you guys get things installed. Once everything is done, you'll have this little green icon down here, and you should be able to go and open up an Xterm window. And so if you do that, and it looks something like this, then I know you're golden. If you're a Mac user, you're not going to be able to do that. You'll have a different set of things to work on, and I'll help the Mac users. Normally they're a minority, and looking out on the audience, I think they're still a minority. So we'll get you guys helped out, though. So now that we've hopefully gotten either the Mac X terminal window open, or if you're using Windows, you've got your Cygwin X terminal window open. This should, if you're using Cygwin, should have a white background. And if you've started the XWin server, you'll have this little green icon. Now, it might be a little hard for you guys to see down here in the lower right-hand corner. You'll have this little green icon, or it might be in this sort of system tray that you could look at. And if you right-click there, you'll see these system tools, and you want to start Xterm. And when you do that, you'll get this, which has the X, or the white background, and the little X logo here up at the top. Now, what server, because again, you have Linux now, so, or something that at least looks like Linux. And so for example, to list the files in the directory, if you type ls, now I can see what files are in my current working directory. But one of the cool things about this is that you have that account on my system. And so what do you want to do if you want to access the Linux server or where your account is? And so that's where you have to know the host name and you have to know your username. So let's just go on. Many of you, well, some of you are in, others are not. But again, let's just sort of see what we can do here, right? And so what time do we end here? 2:50, so not too much time. So the first thing that y'all need to do if you're logging in is change your password to something that you can remember. As much as I love the passwords that I sent you, as soon as they were sent out over the email, pretty much anybody in the world can read that. And so if you're logged in, the first thing you can do is change your password. And so this is a text-based operating system. So everything that you need to do is typed in terms of text or words. And that's the biggest thing that I think most students sort of have to come to grips with as they learn how to use a command line operating system like Linux. Right? When students log into my servers or my workstations up in my lab, they get a graphical interface. They can click on a little Firefox icon and it will show them a web browser. But the primary way that many of them will be interacting with the data and the files on the drive is they will have a window that's much like this, and they'll be typing commands into that window. And so a couple of important key things that is, if you've never used a command line interface before, you'll have to learn. The first is that, at least on Linux, case matters, right? So if you type an uppercase letter, that's going to be different from the operating system's perspective than if you type a lowercase letter. And that's true for file names too. Most of you are kind of familiar with that through file names these days anyway, but it's certainly true on Linux. The other thing is that spaces generally matter. And so if I type, for example, the password command, which is PASSWD, and then I type something after that, it's going to say, oh, that command isn't found. Some of you, when you first type SSH, did dash capital Y or dash lowercase y, that's going to be different than typing SSH space capital Y. The operating system interprets that as two words that you've typed in. And in this case, the first word is SSH. That's the program that you're going to run. And the second word is the dash Y, which is the parameter. It tells SSH to handle security in a certain way. Right? But that's going to be different than if I typed SSH-Y with no space in between. That's going to give me an error that says command not found, whereas if I have the space in between, it's going to tell me how to use the rest of the program. Right? And similarly, if I type PASSWD with a capital W, capital D, it's going to say command not found. On the other hand, if I type all lowercase, it's going to ask me for my password. Now, because Linux has worked at the command line for many, many years, it's smart. Just like you guys put in your password, it didn't show it to the screen, it's not going to show it to the screen here. Right? So if I bang on the keyboard, or even if I type in my real password, nothing is appearing on the screen. And so generally speaking, at a command line, if something is asking you for a password, it's safe to type. Right? It's, nobody's going to be able to look over your shoulder and grab the password. It's just like when you type it into a web browser, you're going to see the little dots appear. So you can go in, you can enter your current password. I'm not going to change my password because I don't really want to. And it'll ask you for a new password. And hopefully it says everything is changed and your password has been accepted. That's important because, again, one, I don't expect you to remember the password I sent you via email. Two, you want to use something a little bit more secure than something that was sent in plain text over email anyway. So that's the very first thing you guys should do. The second thing, though, let's take an advantage or take a look to see what Linux can actually do for us. One of the programs that we're going to be using later in the course is gnuplot. Right? And so I can type GNUPLOT, all in lowercase letters, and I can hit enter, and it will bring up a gnuplot window. And here's the key difference. Many of you may have installed gnuplot when you installed Cygwin, but this version is running on my Linux server. Right? So in principle, if you were to do a long calculation, you could disconnect and it would still be able to run that after you log off, and your laptop wouldn't be using any of its processor to do anything. The other thing is that if I type plot sign of x, it's bringing up a window. Again, this window is originating on my Linux system in the building next door, but it's being displayed here on this display that I have on my laptop. And so that's cool, sort of. But is it useful? So let's try something a little bit more, I don't know, intensive. What can I have you guys run that's not going to kill it? Well, here, let's try this. So type the program in your window, lowercase nmr, capital D RAW. So this is a program that we use to visualize NMR spectra in my lab. Okay, you might, is anybody else getting that message? That might be an error with your computer. If you've installed Cygwin, and you're using VirtualBox, right? Yeah, I'm running VirtualBox. Yeah, so there might be something going on there. It might be that you typed SSH without the -y. No. Okay. So how many people see something like this? This will give us an idea of our success rate. So we got a couple. Not too many. So again, this program is being run on my server next door. And again, you're not going to have any NMR data to look at. But if I've got anything, I've got NMR data. Okay. So here's an NMR spectrum. This is of a protein called HIV integrase. It's not a particularly good NMR spectrum, but it's passable. But the idea here is that I can visualize this spectrum on this computer without ever having to install the NMR processing software on my own computer. Right? And so that's the advantage that this gives you. It allows you to run software on one thing that you might not want to install on your own computer, and or might not be able to, or might not be able to afford, because some software might cost money, or some software might have specific requirements that you don't have on your system. But this is just a simple example of a 2D, and but you can run MATLAB, you can run all sorts of other things on this computer, provided you don't overtax the computer itself. And so this is a pretty simple example. Before we wrap up, a couple other things I want to point out. So one thing that many of you will be doing is running text editors. And so I have a preference of Xemacs as a text editor. It's just the name of a program. And if I start Xemacs, it brings up a window. This works like a regular text editor. And so I can type, hello everyone. I can save it as a text file if I want to do that. We'll be doing this a little bit probably during the Python session. But if you've noticed, if you go back to your original terminal, I've lost the ability to type into the command line. Right? And that's a problem. When something is running in the foreground, you don't have the ability to type into the background. And so the solution that Linux provides for this is the ability to say, okay, I've started to run something in the foreground. Let's stop it and then put it into the background so that I can get my command line back. And so in Linux, there's a very simple way to do that. It's press Control-Z. And you'll notice that it says stopped. And if I go back into my window and try to type something in here, it doesn't work, because this program is basically suspended or hanging in the background. On the other hand, now if I go back to my command line and type BG for background, now it says, okay, this is running again. All those gobbledygook that I typed in the window is now here. And I have my command line that I can run stuff again. And notice again, Xeyes, it's taken my command line, so I no longer have command. So I hit Control-Z. Again, Xeyes is no longer following my mouse. But if I type BG, now I have both the program running in the foreground, but also my command line here that I can type into. There's a very shortcut, or the very convenient shortcut that I can do if I end my command with an ampersand. What that does is it tells the Linux command line to run this program in the background and give me control of my terminal again. Right? And so if I press this, it's going to bring up the X logo. I can do whatever I want to that. But notice that I have my command line still. Right? So this is still responsive in the foreground. I can move it. I can make it as big as I need to. But I still have my command line that I can type into and do what I need to do there. And realistically, running something, pressing Control-Z and then setting it to the background is the exact same thing as running something with the ampersand on it. Okay, we're going to wrap it up here. We're still going to take our 10-minute break. I realize we just dumped on you a lot of information, some of which you guys weren't able to do because the computers weren't working or you got locked out or whatever. That's fine. We're going to hit Linux a couple of times here throughout this session. Anytime I get an opportunity to try to reintroduce or highlight how Linux can be used in a certain way, I'm going to do it so that we get experience. There's no way you can learn Linux. Actually, there's no way you can learn anything that we're covering in this session in a single go, right? And so we're ramping it up. You know, the first session was pretty fluffy if you've had biochemistry before. Nothing against Matt, that's just, you know, how it works. But now we're getting to the point where, okay, this is going to be material that most of you haven't seen or aren't comfortable with. That's okay. Don't be afraid of it. I always tell my group, you know, there's nothing you can type into the computer that's going to break it, right? I have pretty good security controls on this, and unless you're trying to do something malicious, you're not going to be able to break my computer. Similarly, you're not going to be able to break your computer with Cygwin installed. So the best way to learn is to experiment, to play. It's an opportunity to sort of do something new and experience something that you might not ever have gotten a chance to do that, or to do. And so don't be intimidated with it. Just use that as an opportunity to learn. It's just like going back to when you were in kindergarten and you were playing with Legos. You know, this is the same kind of thing. You have a toolbox available. The reason you got to be good at building stuff with Legos is because you made a lot of things that didn't make sense or you know, didn't look quite right. And eventually, you know, the Linux equivalent of that is the computer is telling you, you know, bad command or file name, or, you know, this command, I can't find it. So don't be afraid of that. It's part of the learning process. And we'll go through as we go along and hit some of these Linux commands that we'll revisit and hopefully reinforce what we're doing. Before we wrap up and take a quick break, any questions?